loaded, I think, lights, and I'm going to go ahead and load the industrial assessment, and that just about finishes up that course. I'm going to go ahead and load that. So you folks in energy management are giving that one assignment to complete. That's like halfway through. Then I'm going to give you a take-home final, and it'll take you a few hours. It's meant to be a learning experience. It's meant to, so because you have to look at and find some of the answers, but it's meant to be a learning experience, and that will pretty well finish us up on that course. I did not lecture over controls. I think in the PowerPoint, I just touched on that lightly. And there are a few other things that I'll make sure to get in there. But the bulk of the course is over the heating and cooling systems. That's the bulk of it. There's energy saving opportunities. In industrial is really good to know. Not too many people are familiar with industrial. Believe it or not, industrial is easier because industrial, you look at discrete systems and you treat it as discrete systems because that's pretty much how they operate. Not entirely, but a lot. Whereas HVAC, everything is so interconnected, interrelated. You change one thing, you change another, and it changes this. It's just balancing that in commercial HVAC systems. But it's good to know. Industrial systems because they have dust collectors, air compressors are big things, and there's a lot of things that are used.
Yeah, but we always brought Gary to do our unit controls. We worked on a chiller and cooling tower, and they came in. I think they came in and they put the units in at one time, and they signed a contract for them to keep coming back. Yeah, so that's why we didn't use that.
It's good. It's really good to know where the savings opportunities are. Some are simple things that save people money. I went into one facility once, and I think, according to the EPA, they have to burn off all of the organic compounds. They just can't expel them into the air. And they had what they call a thermal oxidizer. What a thermal oxidizer does, it takes these volatile organic compounds and it burns them. And you have to get them up to 16 or 1900 degrees, I forget exactly. But it's hot.
And that burns everything.
Yeah, that burns all of those VOCs out. And they've got those units now so that the VOC, that's burnable stuff, so that adds to, and they've got a way that they recirculate the air, they bring everything up to that required 16 or 1900 degrees, but then the exhaust is only like maybe 300 or 400 degrees. So, I think some terminology they use that. Very, very efficient. So this one facility, it had a thermal oxidizer, and it ran a lot of chemical processes going on with it to burn the exhaust. So they sent those to the thermal oxidizer. Well, over another part of the plant that was not, they were producing all these VOCs, but it wasn't piped over to the thermal oxidizer. So what they did, they just used that for combustion air in their boilers. Well, they just 365 days a year they put these VOCs into that boiler, but they didn't need what the boiler was producing. It was producing steam. So they just kept venting it off. And but they were burning the VOCs. So I went in there and I said, well, you really know how much you're venting? Yeah, we keep records of it, so that if somebody pounds a steam, they look at it. So I put it in dollars and cents, and I said, do you realize that you are thinking $1 million a year? Say what? Yes, sir. Here's the numbers. Just to burn off your VOCs, you're running your boiler, which you can't use the steam from your boiler, so you just vent it off. They kept records of the vent, and I converted up to dollars and cents, and it's $1 million a year. I said, now, how much would it cost you to duct your VOCs onto your thermal oxidizer, which are already in? Well, we priced it, that was $1.3 million. I said, well, you got a 15-month payback. I think we're going to do that. They didn't realize it was going to be $1 million.
Well, roughly I've been $1.5 million. Right? So, once they goes.
Yeah, it was $1.3 million to pipe it over there, the duct work. That's a no-brainer. No-brainer, so. You can be a real hero, and
some people have a hard time opening that billfold up right at the beginning, It really doesn't even matter how much you tell them, but sooner or later they're going to realize, man, this is starting to make sense.
When you put it in terms of dollars and cents and payback and internal rate of return, you get people's attention. Well, when you put things, there's certain ways that you put internal rate of return in there. So he says, well, if you put your money in the bank, what are you going to get? If you're real lucky, you get 1%. But you can put your money into upgrades and get, let's see, I just did one that was 158%. I wish I could get 158%. So, yeah. Well, that's you got to present stuff so that it gets their attention. Okay, I want to go into wind. Now, this is a wind resource map. And you can't see this, but I think I've got a little bigger on the next page. And it tells you what the average wind is at certain locations. But the important thing that you have to look at wind maps is elevation. You have to look at elevations. If you look at one that's at 10 meters, it's a whole different picture if you look at one that's 30 meters or 50 meters. So you have to look at the elevation. Now, I think, here's the number. Here's the average speed. This is a color code that goes with this. I just blew this up. It has wind power density, and then it has wind speed. And I think that's at 10 meters, and I think this is at 35 meters. I can't really read it, but at any rate, it's higher. Here is another wind speed map. Looks totally different. This is at 80 meters. This one, I think this is at 10 and 30, so it's a different picture. So you get a different picture when you look at different elevations. I always like to ask a question. If I went an area, and if I had wind at 10 miles an hour, if I had wind at 20 miles an hour for half the year, 180 days, and 0 for 180 days, so 20 for 20 wind speed of 20 miles per hour, we'll call it 20 miles per hour for 180 days, 0 miles per hour for 120 days. Or if I was at a location that had a wind speed for 360 days of 10 miles per hour, which one do you think would give you the most wind energy?
Half the year.
Why?
Because sure, it may not be quite as long, but the amount of wind that's being blown, it's a lot higher. So I think based on the number of how high, how fast the wind is going.
But it's going zero for the other half of the year. It's gone zero.
I know. But I see.
They both average year round of 10 miles per hour. Yeah. Which one would give you the most energy generated?
This could apply to almost any turbine. Half a year 20, half a year 0, or all years.
Where's your highest?
That's turbine design. But as far as the potential that you can get out of the wind, be able to get more out of the wind with the properly sized turbine, 20 and 0, and 10 year. I say all year long. And what do you say? All year round 10. And you said
Half.
half of 20, half of 20, half of 0.
Mm-hmm.
Who's right?
I'm right.
And I'll show you. Why.
Huzzah!
I'll show you. It's not proportional to wind speed. That's why when some people look at the average wind speed in a certain area and try to make a judgment call, and you can't do it. You can't predict what your production from wind turbine is going to be from the average wind speed. And I'll show you the number. This is an old one. This is 2007. Now we're 10 years later. We have a lot more wind capacity in Ohio. Too bad we don't have a whole lot more. You folks are aware of the change in the setback ruling for wind turbines? Okay. This was 3 years ago, 4 years ago. Time flies. At any rate, in the Farm Bill, which has nothing to do with wind, in the Farm Finance Bill, State of Ohio, they slipped in a sentence that changed the setback rules for wind turbines with respect to property lines. No public scrutiny, wasn't presented, nobody got to see it, it just slipped right in. So when that was done, that eliminated an estimated 90% of the locations for wind farms. Eliminated 90% of the area, the ground. Couldn't put wind turbines on. Nobody got to talk about it. Now we talk about wanting jobs in the state of Ohio, and the state of Ohio invests, don't let this leave this room, $5 million in a UAV center because it might create in Indiana and Ohio 2,500 jobs by 2020. So let's put $5 million into that. Now, one clause in that farm finance bill stopped over $4 billion worth of wind farm. There was $2 billion that was shovel ready to go. But there was a clause also in that sentence that said, if we grandfather you in if you have your permits, except if you move one turbine location, it goes back to the new rules. So people, these people that want to invest in these wind farms, they just walk. They said it's too dangerous. It's too dangerous, so they walk. And there was another over $2 billion worth of wind farm that was almost ready to be permitted. Yeah, I guess. So we lost over $4 billion worth of work in the state of Ohio. Tens and tens and tens of thousands of jobs. And yet, they say, well, let's put $5 million in UAVs, that might give us, in 2 states, 2,500 jobs. Where's the thinking? Where's the thinking?
Pardon? They do it all the time. They say something in these bills all the time that nobody even knows about. Why hasn't somebody changed that?
Well, there's been big arguments to change it, but there are some utilities that are fighting it so hard, and they have so much money and so politically connected that so far have been able to turn it. And we have a viable wind resource up in northwestern Ohio. And if you go up there, you'll see a lot of wind farms that are already built. So, and then I've heard, what is it, Amazon that wants to come into the state of Ohio and build a big warehouse and distribution center. But they said, well, we want to operate totally off of renewable energy. And so if we can't buy it from you, we'll buy it from Illinois and Indiana, you know? I'm not real sure. I think so, but don't quote me on that. Don't quote me on that. But there are a lot of companies that want to operate the facility totally on renewable energy. And so, the state of Ohio is losing. We have really backpedaled a long way. Other states are going forward. We're going backwards. We're going backwards.
Is that the pump up the coal?
Yes, because we all know our salvation is coal.
Yes, I mean, he's doing that, he wants the coal.
Well, in the state of Ohio, there are, I just heard this number, I think I remember, there's about 2,500 people in the state of Ohio in the coal industry. 2,500 people. So there's 110,000 people working in renewable energy efficiency. Give me a break.
The thing about coal, it kills me, is when I went back to school several years ago, coal was out of way off then. When I was in school with everybody that was getting laid off from coal 20 years ago. So, what, now you're going to do it all in roofing?
And then, we talked about all the jobs that are being created. There was like 800 jobs created in the coal industry nationwide. Give me a break. 800 jobs? That's nothing. Down in southeastern Ohio, yeah. That's where the coal. And, if you use that thinking about let's try to save coal, we'd outlaw the car, we'd all be riding around horse and buggies. because the car put the horse and buggy people out of work, you know? It's just, it's not much different, you know, not the way I think, so. Oh, well. So this is an old map, and I need to update that. And when we look at wind turbines, there's this big wind turbine, which we call it. This is a utility scale, and these are what you see in these big wind farms. That's about 300 feet from the ground up to their hub, and these are maybe 200 feet diameter, huge. Then there are like industrial and commercial wind turbines that are a little smaller, and those are primarily for a facility. and if you go up and take what is the beltway that goes around Columbus? Is that 270, is it?
Yeah.
And when you're going up, if you look off to the west, you'll see there's a turbine that's like this. It's and I don't know what it's attached to, but anyway, it's there. And then you have a residential grade. So huge, big, and small. If you go out on west on 40, out to Dole Farm, he has he has 10 kW Berkeys there. And that's what this shows.
You can't just build it. I mean, you gotta, because it's so tall, there's not places you can find out to put it in.
You have to be so far from the property line, and there's permits and zoning and blah, 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 yeah.
Those, are they all self-sufficient, everything was run off those women
On which ones now?
out of Dole?
Dole? No. He's got, I'm forgetting, what does he have, 6 of them? They're 10 kWs. Then he also has, on his little museum there, he has solar PV on the back of it, facing south.
Really?
So he has solar and wind. And really, I think he gets more out of his solar than he does his wind.
Yeah, my daughter worked out there for a few years.
Oh, did she?
Yeah. They hire the kids during the summertime. And I used to pick her up and I saw those windmills.
Yeah.
I said, wow.
But just be curious, what the big wind turbine, make a price, what's the price range?
I couldn't tell you. I can tell you, I went to the facility that built these poles, not called poles. They built these. And that was something to see, because they roll this huge thick metal in a kind of a conical, and then they weld them together, you know. And
Were they produced in the U.S.? They were produced in the U.S.?
yes, it was up in Michigan, right next to the Great Lakes. So they shipped them on barge.
I was in Charleston, South Carolina, and I Civil War submarine, well, right across from it, there's this huge blade. We didn't even know what it was when we first went by. And it sits in the parking lot. And the building across the street is an energy. We didn't notice that until we come out. And I said, well, this is off a wind turbine. So then I saw the energy on that building.
Oh, man.
They're huge, the blades.
Yeah.
I couldn't believe how big it was. I mean, just to drive by and see them turn them, you don't really.
No, they kind of, you lose perspective of just how big they really are. Yeah.
Especially when you've got a big field, when you got a whole, like over in Indiana. I think it was Indiana I was going through.
Oh, yeah.
It's constant.
Yeah.
It's always warm. You can't tell how big they are unless you're standing next to one.
In Canada,
I was just gonna tell you, it says $1.6 million for that deal.
1.6 million?
On the bottom of that thing. And that's whenever that was installed, cost about 1.6 million.
Why I ask, because I go back home and there's like famous jerk stuff on home, or like all the music and stuff. I saw that guy would like what display some like.
This is in Michigan. These are probably some earlier ones, you can tell by the mass, and these are some later ones, but they're all in one wind farm. Wastewater treatment plant.
You probably have gone over this, but I never can write my head around it. So, go back to the thing that said it generates like 1,650 kW.
Okay.
And I know it says that's enough to power about 475. But I don't understand converting the fact that it can produce that many kW, but how many kilowatt hours?
Okay. Normally, these are rated, they have what they call a capacity factor. And if the size of this is 1.6 million watts, because that's 1,650 kW, it's not producing that year round. So sometimes it's producing maybe that much, that's its design, and sometimes it's producing less. So it may have a capacity factor of maybe 0.35 or 0.4. So it's only whatever it would produce is maximum at its rated. Maybe it's only going to produce 30% of that or 35% of that. So, and it's just the kilowatts multiplied by the hours of operation. On wind turbines, I think you'd count like 8,760 hours a year. That would be their rating. So you take 1,650 kilowatts times 8,760 hours and multiply that times its capacity factor, which might be 0.3, might even be as low as 0.2. But we can run some of these on red screen and see what the capacity factor is, and it will tell us how many kilowatt hours that'll produce a year. So we'll do that. Yeah, we'll do that.
On those larger ones, are they hooked right into a grid?
Yes.
They don't store any of that energy?
Nope.
It just
Nope.
goes
Right into the grid. And there's different types of controls here. Of course, you know, our grid operates at 60 cycles. Well, this operates, and these are three-phase. These are three-phase. But whatever cycle is depending on how fast this is turning. So what they do is they take the AC that convert it to DC, and then they take the DC and convert it back to AC, so it's the proper cycles. And that's the same thing our wind turbine does. Our wind turbine produces whatever cycles it's turning, but then the control, there's a rectifier up in the wind turbine that changes at the direct current, because that's an alternator up there. It changes at the direct current. The direct current comes down here, stored in the battery, doesn't have to, goes into the inverter that changes it back to 60 cycle. So in some of these big wind turbines, probably the most popular does that. Then there's some that are synchronous that their windings are their windings are activated, excited. They're excited by the grid, and the grid is on 60 cycles, so it will produce 60 cycle. There's about 4 different types of generators.
So that wouldn't have to change that.
No, that wouldn't have to change back. So there's about 4 different kinds, and probably more. And here's a big wind farm. That's in Michigan. Here's one in Utah. They go up in some of these valleys between these mountains where that wind really goes through. And that's a good location for excuse me, wind farms. Got my voice back, but I'm not rid of the cough yet. This is Ohio, and it shows Ohio has that decent wind resource up here. Now, one thing about wind resource, down here in the Dayton area and Dayton and surrounding area, we say, well, we do not have that much wind resource, and we really don't. That doesn't mean that you can't go 5 miles outside of town, up on top of a big tall hill, and have wonderful wind, even though the average Dayton area doesn't have that much wind resource. So it's like real estate, location, location, location. And you really have to test, do a wind survey before you put in a wind turbine. This is Cleveland, Great Lakes. You get a lot of wind coming off the lakes. This is what a small wind turbine, a power curve looks like. There's a kick-in speed. This says 4 meters per second, about, where it kicks in. Then you have some design speed where it reaches its maximum production, and it starts tapering off. And these are different type of turbines. So really you'd want to operate right here. On small turbines, their blades are stable. If you notice on those big utility scale turbines, their blades will rotate. And they rotate, and they can control what you call the attack angle of the wind, because that attack angle changes. If you got your wind going in this direction and you got your blades going in this direction, then the angle of which that wind is hitting that blade is not this way, it's this way. So they can change the pitch of that blade to control that attack angle depending on the direction of the wind and the speed of the wind and the speed of the blade. So not real straightforward. We won't learn that. We in this class we're aware of it. That's as far as we go.
They would fix those blades if they lost their engines. They would bring that helicopter down probably about 45 miles an hour.
Yeah. Just by controlling those blades, pitch. Yeah. And this is another typical curve on a small wind turbine. And this was a short lesson. I'll go on to the next one. So that was more about wind resource, and this gets into more about turbines and performance. And this is a horizontal axis, 3-blade horizontal axis, and this shows that this particular design probably has blades that will turn so it can control that attack angle of the wind. Horizontal axis, and all of our utility scale wind turbines have horizontal axes. Our wind turbine has a horizontal axis. A lot of small scale, this is a Berkey, a lot of small scale wind turbines have that horizontal axis. So it's really the more popular style. Hmm?
Like what's back there?
That's horizontal. We got one on the roof, and that one there was on the roof, and it fell down.
What they also nicknamed what was, or they also nicknamed fishtail. What they also nicknamed fishtail turbines.
For the tail,
Yeah. They certainly do have nicknames. Like that.
and
one's
calls
called-
it the furl.
Yeah.
We'll go there. I remember when almost every farm had one of these when I was a kid. Yeah, I'll get my pointer back. You probably remember these, don't you?
Yeah, from cartoons. Every cartoon is supposed to be
I remember for real, not cartoons. Not cartoons. This is a vertical axis. A lot of people are looking at vertical axes because it does not have to change direction as the wind changes direction. And then they can also get a lower kick-in speed. That's a vertical axis. Here's another type of vertical axis, but it's more helix.
You see those sometimes around
Do you?
there. Yeah, but they put their little jets on it to make it look like it's part of the ocean.
And here's another vertical axis. Now, I know all of you know the formula for kinetic energy. You remember that from physics, right? Kinetic energy, and that is energy like a gallon of water is a gallon of water. 1/2 mv squared. So kinetic energy is a function of the velocity or speed, if you wish, squared. But we went power. And I think we went through, remember, power is energy per unit of time. So we have to divide this by time, per unit of time. So let's just put mass flow rate. That's mass per unit of time. V stands for velocity. M dot stands for mass flow rate. Mass flow rate is a density times the area times the velocity. So and then power, if I take this rho times the area, that's the sweep area of the blade, times the velocity, and I substitute it back into this equation, I get 1/2 rho a velocity cubed. Velocity cubed. Let's do a little exercise.
You folks got a calculator with you?
Yeah.
I'm gonna write down 10 feet for a second. I'm gonna leave this up. 8, 6, 12, 15. So,
Do me a favor.
give me the 1, 2, 3, 5 of these. Give me an average of 5. Average equal to. Then I want you to give me the average, the cube of, I want you to give me the cube of the average. take the average, whatever the average is, and I want you to cube that. Then I want you to give me the average of the cube. One, we take the average. Two, we take the average and then cube it. Three, you'll cube these and take the average.
Yeah, is the 10 part of the average?
What?
Is the 10 part of the average?
Take the average of 10, 8, 6, 12, and 15.
Okay.
Add them up and divide by 5. You take the cube of the average,
Yeah, which is basically just cubing the average.
and then take the average of the cube.
Yeah, so whatever you have cubed, you just divide that by
261.2 cubing the average.
What'd you get?
1061.
2,061.28.
my God.
Average
Yeah, 41 for the average, the simple average.
plus 8 plus 6 plus 12 plus 15 plus 5. Average, I got 10.2.
Oh, sorry. I forgot you looked like that.
If I cube average, I get, we'll just go 1061. If I take the average of the cube, then what you do is you add all your column on the right.
I cubed,
That by 5.
right.
This is the average. This is the cube of the average. This is the average of the cube.
How do you get down to just the cube?
Because I took
10 times 10
10 to
times
the
10.
third power, 8 to the third power, 6 to the third power, 12 to the third power, 15 to the third power. Add them up.
Okay, because it's a cube.
Yep.
least have a score for some of this stuff.
Now, if we take this, which is this equation without the area, we call that wind power density. Wind power density. And since we're in feet per second, then I have to say 1/2, and the density of air is 0.075 pounds per foot cubed. And the velocity cubed, which would be this is 1366 feet cubed per second cubed. And I have to go through the units on that. I have to divide this on 32.2 feet per second squared. In our system, we have to take our pounds, mass, and divide it by gravity. In the Systems International, you don't have to do that. You call it wind power density.
That's the thing.
1/2 rho V cubed, yeah. Now, this is the maximum power of the wind, but you can't capture all of it. Theoretically, you can only capture 59% of it. Nothing is 100% efficient, so theoretically, we can only capture 59% of the power of the wind. So remember that, 59%. This is just some examples of some different wind turbines. This goes to some calculations because I know everybody loves calculations. So this starts off, you've seen this before, and this, 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 and this. And this is where we developed this wind power density, and we said we can only capture 59% of it. Get through this part. There are different types of wind turbines. We have utility scale, industrial scale, and residential scale, which we went through. Utility scales are now in megawatts, huge. This is 2 megawatts. That's a utility scale. And I need to update this.
This was,
Look at the blank space.
don't have any.
No, we use wind turbines.
Mm-mm.
I think Ford would definitely should.
Hurricanes would blow them down.
So make them stronger.
So this is utility scale. This goes up to 13. And, you know, we have a lot, nationally, we have a lot of wind turbines. We used to lead the world, but China passed us up some years ago. This gives you identification of the different parts. You have blades, the rotor, the pitch, brake, low-speed shaft, gearbox. These have gearboxes in them, and the gearboxes are high maintenance. Generator, different types of generators, controllers, wind speed and anemometer, wind vane. This whole big thing up here is called a nacelle. These are as big as buses. They don't look like it, but they're as big as a city bus.
On my way down to Chicago, my family drove through a turbine field. My sister was like just in awe, and I was like, yeah, you know these are, right? She said, yes, I do. I was like, you weren't saying these as large orders. She said, no, I was not. I knew there would be big and large, but man.
This is a type of generator in a utility scale wind turbine. Asynchronous induction has a transformer, and this is a synchronous generator. This is a synchronous double feed induction generator. Don't ask me to explain that. Get electrical engineer in here. And this is a synchronous unsynchronized. And this is a synchronous synchronized. So just be aware that there are different types of generators. We won't go into great detail about those. Here's an industrial scale we looked at before we looked at utility scale. So this is an industrial scale. And then we have a residential scale. So we started off, we divided them into utility scale, industrial scale, and then residential scale. On a residential scale, they have an alternator. And then the alternator, that is the alternating current is converted to DC and then converted back to alternating through the inverter, just like on a solar PV. There's a controller, wind speed. So the wind turbine produces three-phase AC that varies in voltage frequency as the wind speed. Controller rectifies the variable AC back to DC, and then it's inverted back then to 60 cycle AC. Residential alternator shows that alternator. This shows the airfoil angle of attack that I referred to. That angle of attack changes as the speed of the turbine changes. This is an anemometer, measures the wind speed. We have one up on our mast. Go over there and see what our wind speed is. Up on that upper box, see if we got any wind out there today.
This is a great fire. That's a great fire.
Come down the corner of Second and Wilson. That wind right there on that street, you can walk a lot of way. Towards the courthouse. Nothing.
Then this is glossary of terms. That's angle of attack. That's the relative direction of the wind with respect to the blade. Now, the Betz coefficient, that is that theoretical 59% that is a maximum possible energy you can obtain from the wind. Braking systems in them. Cut-in speeds. This is a cut-in speed on this particular example is 3.5. Dump load, that's like our heat sink back there. That's that aluminum thing that's hanging on the side of the building. If our wind turbine is producing current and the brakes can't stop it and the batteries are fully charged, it will divert the load to that heat sink that you see back there. They call it just a dump load. That's just something that eats up your excess electricity. Then we have furrowing. If you look at this turbine right here that's sitting here in the lab, it's hinged. When the wind speed gets to be a certain speed, which that's over its design speed, what it will do is it will just collapse and the blades will then be parallel to the wind and they'll quit turning. They call that furrowing. They just collapse and sets the blades parallel to the wind, so they no longer face the wind. That's called furrowing. You can see here where it's collapsed. That's a tail, and that's a furrowing tail that's on the back of that. Probably. I'm sure Russ could tell us that.
Maybe you should bring away one of the classes.
Russ spends his summer sailing. HAWT, horizontal axis wind turbine. Most popular type, 3-blade. Nacelle, that's that big bus-sized piece on the top of a utility scale turbine. Has all the components inside it. Tip speed ratio, this is a little hard to see, but this is at 59% curve. Well, that's theoretically the most energy that you can derive from wind. Well, we never hit that. So this is different types of turbines. This is a 2-blade. This is a 3-blade. And you can see that they can produce a peak power at a different tip speed to wind speed ratio. And then you have this type, which the maximum it can get is about 40%. The maximum of 3-blade is probably about 48%. 2-blade might be 46 or 47%. So that's these different blades, different configurations of wind turbines, and the percentage of the maximum available power of the wind that they can take advantage of. Here's a tower. In the vane, large flat piece of material used to align a wind turbine rotor correctly with the wind. Could be mechanical. It could just be like the tail on those R turbines. Vertical axis wind turbine. Since we're dealing with electricity, volt amp, that's simply the volts multiplied by the amps without factoring in the power. Who knows what a power factor is? If you have like electric motors in a plant, those electric motors, because of their windings, they store and release energy, So what happens is,
Here's the power coming from the utility company. Here is my voltage. This is voltage. And here is my current. It doesn't have to be that. So this is voltage and this is current. The utility company charges you for watts, which is voltage times amps. So this is maximum voltage times maximum amps. That's what they charge you for. If you have certain equipment in a facility like electric motors or what used to be the old ballast for the OT12 lamps, anything that has coil windings, if you're familiar with electricity, those coil windings in AC electric, they store energy and release energy, store energy and release energy. So if you have those, most facilities do, then what happens is, here is your voltage. I'm trying to draw that the same as that, but the amperage gets out of phase with the voltage. So now, when the utility company charges you for the volts times the amps, they don't get to charge you for maximum voltage times maximum amps because they're now out of phase. So now they have to charge you for this, which is a whole lot less. They don't like it. They don't like it a bit. So what you can do is you can put capacitors. There's capacitors on some motors that'll bring this back in phase. There are some facilities that have big capacitor banks coming in, and those capacitors will bring this back into phase. Most
utility companies, if you get a power factor of 0.9 or less, they charge you. Because they're losing money. They're shipping this and getting paid for this. That's power factor. Your voltage and your current go out of phase with each other. So one's at a maximum here, the other's at a maximum here, but the power companies ship maximum together. And your facility pulled them out of phase. So they don't get to charge you as much.
If you guys ever said that to me, I was ready to tell you, I would make no such promises.
This is an array of batteries connected in parallel and series. I think we've gone through this before with the solar PV. Oh, what is the power of the wind? The 30-foot diameter wind turbine. If the wind velocity is 30 miles per hour and the air temperature is at what's the base limit? See if you can calculate that. Only the density of air is 0.075 pounds per foot cubed. Then you have to divide that by 32.2 feet per second squared. See if you can go through that calculation. I'm going to take a little break.
Yeah, 6.3. I got 6.3. Because I have to be at work tomorrow by 9 or 10. And it takes a long time by bus to get over there. It's like half an hour, man. I told my best girlfriend that my next class either ends at 8 o'clock or 8:30. She said, which Wednesday, most times it ends at 8:30, so she can let me down by 8. And she says, if the class ends at 8 or 8:30, I'm straight up leaving, even if the professor's talking. I'm like, okay, I want to do that, but I can't. Yes, it will.
You have plenty of time.
Oh, I got plenty of time. So let's see it right now if I wanted to. I hate walking outside when it's cold out. Now walking here to the hub, which is only like 10 minutes or less from me. Not that far to walk. Man, it's too much when it's cold out. Just to the hub down that way. It is a 30 minutes, about a 40 minutes bus ride. But if I have my own car, it would be like 1.5 hours drive. Or less. If I stay on Main Street. Just by avoid Main Street because too many stoplights, and I don't feel like dealing with that many stoplights. Sleep right now. I lost my voice. I'm like, not at all. Wait, I nodded off that long. Yeah, yeah. I just mean when you're overboard, you just go towards where the hospital is, and then go up Salem. All the way down until I see where Big Lots used to be, go through the parking lot, go through the back of my neighborhood, and I'm home. I could do that. Actually, that's what I'm gonna do. I need my car. Screw me thinking, man. I'm just gonna cut through a parking lot, to avoid all that traffic. I might get a ticket for that. I might,
Out there, you might.
yeah.
But them cats sitting in the parking lot.
Hey, if I see a cop, I'm saying I'm cutting through it. I see a cop, I'm just gonna pull over, get out, go on down the street, grab one soap, one thing, walk right out, and continue on my way. If they give me a ticket, still, but if they still give me a ticket, but sometimes I'm leaving and give me a ticket, I'm not paying for it. Oh wow.
Figure it out?
6.3 is what I have.
6.3, was that $1 million?
I did not depreciate that to you money. I just appreciated
Everything has to have units.
if it was 6.3, I would have that person convince me to give me at least 10% of that.
Let's see. We have a 30-foot diameter, so we want to use it for one,
Oh wait, hold on. How is diameter of P?
so 1/2 density is equal to 0.075 pounds per foot cubed. You have to divide it by 32.2
30-foot diameter. So we have pi, 30 squared foot squared, pi v squared over 4. And our velocity is 30 miles per hour. That's 30 cubed miles cubed per hour. I'm going to have a hard time fitting all this in here. There are 5,280 cubed feet cubed per mile cubed. There are 3,600 seconds per hour. I should have put the second. So if you do all those numbers, the mile cube makes it the mile cube. The hour cancels the hour. The foot squared. So the unit should be foot pounds per second. What number do you get?
You got me, you lost me.
You lost me, man.
Oh, come on, this is just algebra. This is third grade algebra. I didn't need to say that, did I?
No, no algebra.
Just take, got a calculator? 0.075, that's 3.14, 15927, times 30, times 30. Times 30, times 30, times 30. 53, times 53, times 63. Divided by 3,600. Divided by 4, divided by 32.2, divided by 6.
What is it, 32.2?
That's gravity. See, if we say if a car weighs 4,000 pounds, that's not its mass. Mass will stay the same on Earth, on Mars, on the Moon. But when I say 4,000 pounds, that's with Earth's gravity, so I have to divide it by Earth's gravity, so I have the mass. And Earth's gravity is 32.2 feet per second squared. That's how fast you accelerate. You jump off the building. Or
or drop a rock. See if you can go through these numbers. The units are right. Foot pounds per second. Then we're going to do something else with that.
Just tell me,
I will be good.
Nine 9.09 See if that's what you got. I'm going to check myself here.
Is that 10 inches?
Yep. 9.09 times 10 to the 11.
Did you say you got 1.97?
Pardon me?
Did you get 1.97?
I got 9.09. I rounded it up. It was 9.089. I just rounded it up. So we divide that by 550 and multiply by 0.746. One 1.2 times 10 to the 9th kW. See if you get the same numbers I do, in case I made a mistake.
Yes, I've been making a mistake. It's 30 miles, that's cube, 30 cube, hour cube. So actually 3,600 cube per hour cube. So gotta take this number divide by 3,600 twice. See? $70,124. See if you get 70,124. You got to get the same. Got to keep doing until you get the same number twice.
So the calculator.
0.07 multiplied by 9, multiplied by 9, multiplied by 30, divided by 2, divided by 32.2, divided by 4, $70,124.
That's 4,075 times 5 times 900 times 27,000. Okay? That's 30 cubes.
Divide this by 550 foot pounds per second per horsepower, 0.746 kW per horsepower. That will give us then the kW. So we divide that by 550, multiply by 0.746. It's 95 kW. So that's the maximum power of the wind.
So if I have a turbine with a 30-foot diameter blade, and it's in wind at 30 miles per hour, the maximum that wind power has is 95 kW. The maximum power I can get from the wind would be 0.59 multiplied by 95 kW. So it's 56. kW. That is a maximum theoretical power that I can extract from that wind with a wind turbine with a 30-foot diameter blade, and the wind is at 30 miles an hour. So let's back up here. We have, how many blades did I say it had? A two blade. So let's go back here. This is a two blade. Well, a two blade, I can't get 0.59. I can only get maybe 0.47, about 47%. So in reality, from this, I get 0.47 times 95 multiplied by 0.47. I'm going to call it 45 kW. So I just wanted you to kind of get a feeling for some numbers and magnitudes. I don't expect you to work these, but kind of understand where it came from. We used this equation, 1/2 rho AV cubed. 1/2, this is the density of air divided by gravity. Area of the circle is pi v squared over 4. And the velocity is 30 miles per hour, so that's 30 miles per hour, that's number one state. The rest is just units conversion. So the maximum, the power of the wind is 95 kW. I can't capture all the power of the wind. Theoretically, the maximum power I could extract from the wind would be 56 kW. But since I have a two-blade turbine, the maximum I can extract from the wind is 45 kW. A little less than half. That's a pretty big turbine. So this is the important number to remember. It's not proportional to the average speed. It's proportional to the average of the cubes of the speed. And that's the wind power density. So if someone wants to talk about average wind speed and production of wind turbine, you know that's not the right number. You want to look at the cube of the speed, and they call that wind power density. Wind power density. So I think I ran through all of this. There, 95. 56, that's the maximum theoretical. And 45 kW. So that's the answer we got. And I'm not real interested in your calculating that wind, but if you do go through, just to show you, this is it's called the advanced ratio. That's the tip speed over the wind speed. So we go right up in here under this 2 blade and we say, well, at the maximum power, that's probably, that ratio is 10. Means the tip speed over the wind speed is probably about 10. So we go through the calculations, and that will be about 294 revolutions per minute.
That's a lot for those big blades.
What is that? Is that about 5 revolutions per second? That's getting with the program, isn't it? 5 per second, 60 seconds per minute. Yeah. Another thing need to be aware of, that we all know the farther you get above the surface of the ground, the higher the wind speed. So there's a nice little formula here that you can use to calculate the wind speed, and it's that the velocity at some new elevation over the velocity at some known elevation is equal to the new height that you want to calculate the wind speed at divided by the height that you know the wind speed, and that times some exponent. That exponent is a function of whether you're over ice and water, or if you're over low grass, or if you're over a rural area like houses, or if you're over suburbs. It controls that exponent. If I knew the velocity of the wind, let's say it was 5 miles per hour at 30 feet. Walking up speed at 100 feet. So let's say it's over a grassy area. So I would say that the new speed over 5 miles per hour is equal to, I knew this at 30. I want to know what it is at 100. And since it's a grassy area, I mean, that's 1.014. So I take 100, divide that by 30, take that to the exponent of 0.14, and multiply it by 5 miles an hour, and I get 5.9. So at 100 feet, it would be about 5.9 miles per hour. And this goes to the wind power density. I'm not going to have you calculate that. We can go through and calculate, what would that calculate? At 80 meters, we calculate The speed associated with the wind power density V was 7.11 in the Dayton area. And that's not a homework assignment. I don't expect you to do that. Any questions? I just want you to develop appreciation. There are different size of wind turbines. Utility scale, industrial scale, residential scale. There's horizontal axis wind turbines. There's vertical axis wind turbines. The power of the turbine is proportional to the cube of the speed of the wind, not the average, but the cube of the speed of the wind. And we can calculate or estimate what the speed of the wind is at other elevations if we know what the speed is at certain elevations.